Okay. So today the topic is E2 elimination. Does anybody have any questions to start with? And then
I had a question about the diaxial elimination. I just kind of confused about what they were talking about, like the problems that they were using.
oh, so this is with cyclohexane rings?
Yeah.
Okay. Anybody have any other? So I'll kind of mix in the...
I was just going to say like the Hoffman thing, but I'm probably
Oh, yeah, the Hoffman. Okay, so Hoffman elimination. And then there's rings and open chain systems. So let me just start with just a little bit of background so we're all on the same page. So E2, the difference between E1 and E2 is E1 has a carbocation. And E2, in an E2 reaction, what I'm going to do is I'm going to have my leaving group, I'm going to have my beta hydrogen, and what I'm going to do is I'm going to take a strong base that's going to come in and rip off that hydrogen, causing the pair of electrons to move and the leaving group to leave. So if you didn't have the base there, and you had a carbocation, you'd be E1. But what I want to stress here is the idea that when you have a carbocation and we're losing a beta hydrogen, sometimes the book will write, they'll have a water molecule or they'll have something there that comes in and sort of grabs the hydrogen so then the pair of electrons can move to form the double bond. And sometimes you'll see this, I guess I write it as a dotted line, sometimes you'll see them write it as a full arrow. And the reason that I don't usually show the water molecule coming in and getting the hydrogen is because I want to make the point with E2 that this base is active. That base starts the process by coming in and ripping the hydrogen off. The water doesn't rip the hydrogen off. The water, this H+, it leaves. The water catches it. The water's not aggressively coming in and pulling that hydrogen off. The base, it's coming in and aggressively pulling that hydrogen off and starting the process. So one difference between E2 and E1 is that the base is necessary. So if we use a strong base, it's always going to be E2. Always. Primary, secondary, tertiary, always going to be E2. Okay, we'll get to what kinds of bases in a few minutes. Okay. So that's one of the difference. The other difference is carbocation versus no carbocation. So in terms of the E2, the other difference between E1 and E2 is geometry of the beta hydrogen. Everything is about removing the beta hydrogen in elimination. That's what I'm losing, is the beta hydrogen to form the double bond. So in E2, there is a specific geometry that beta hydrogen has to take in relationship to the leaving group. So if I have my carbon, and I'm going to write it from left to right, and I have my leaving group, my hydrogen must be, and now I'm going to go ahead and put it in a sawhorse representation. This hydrogen and this leaving group must be anti. So that if I was looking at this molecule down the carbon-carbon double bond, my Newman projection would look like this. My beta hydrogen and my leaving group. And remember, this is a beta hydrogen because the leaving group carbon is alpha, and then the carbon attached to the alpha carbon is beta. The hydrogen attached to the beta carbon is beta hydrogen. Okay. So that hydrogen must be anti to the leaving group, and this is actually what is called then the anti-periplanar transition state. And I think the book, there's been another terminology that's come into vogue, and I forget exactly what it is. It's not diaxial. I'm working towards that. But I call this antiperiplanar. Well, coplanar means that they're in the same plane. It doesn't mean, coplanar would mean like the hydrogen and the leaving group are in the same plane, but they could be in the same plane if the hydrogen and leaving group were eclipsed. So coplanar is just coplanar. Antiperiplanar, which is periplanar means coplanar. Antiperiplanar means anti, and they have to be anti to undergo E2.
And what's the purpose of having them?
Well, that's a good question, and it's a little more complicated question. So they have to be antiperiplanar because that leads to the lowest transition state energy. And here's how that works. First of all, let's write the transition state. So I have my base, just my generic base minus, and up here, let me just again write base minus coming in, grabbing hydrogen, pair of electrons moving, leaving group grabbing its pair of electrons and leaving. So this would be like the first step in the E2 reaction. Then the transition state would have the base partially bonded to the hydrogen, partially on its way out, and then a partial double bond forming, and then a partial bond to the leaving group. And then I would have my bold wedges and my dashed wedges distinguishable from my dotted lines. So the transition state would have my base, and I need to take that minus charge away, would have base bonded to hydrogen, breaking the CH bond, forming the CC double bond, breaking the C leaving group bond. So that would be the bond breaking and making in the transition state. So it's a little more complicated from the standpoint of now I've got a base that's pulling off the hydrogen, but I'm using the same rules. Partial bonds to indicate the bonds that are being broken and made. Now, as far as the charges go, the base has a delta minus charge, the leaving group has a delta minus, because the base is delta minus charge, or is minus charge. The leaving group, when it's all said and done, will be. So that's going to form a double bond, a leaving group minus, and a base that's been protonated. So this is the antiperiplanar geometry of the transition state. So the H must be anti to the leaving group. Now the nitty-gritty reason for this has to do with energy, and it has to do with what I'm looking at. So when I'm looking at this transition state, I am looking at an sp3 hybrid orbital that the hydrogen is attached to. Then over here, I have another sp3 hybrid orbital that the leaving group is attached to on that carbon. Okay. And so if you can imagine the base coming in and taking the hydrogen off and where the molecule needs to be, here's where it starts, and then here's where it ends. So it ends with a pi bond. Now what happened to those orbitals as we're going from here to here? And what's happening is that those orbitals are starting out like this, big lobe, little lobe. They're going to shift to become parallel, and then it's going to form the double bond. So as it shifts over, the big lobe is going to be feeding electron density into the little lobe. And as the leaving group leaves, it's going to be taking the big lobe density away. Actually, if you think about it shifting, it's going to be shifting with this with 2 pair of electrons and this with none overlap to form the double bond. So for the hydrogen to have to be, it has to be periplanar because that's the easiest movement to get to the transition state. And the less movement you have to get to the transition state, the lower the energy of the transition state. Okay. So I think I turned on the document camp. So I do have. Okay, so as the base comes in and grabs the hydrogen, the orbitals will swing over. Oh. So the orbitals will swing over, they'll begin to sort of even themselves out, and then once they become parallel to each other, they'll form the double bond. So anything, so if the leaving group was like this and the hydrogen was like this, I would have to physically move them to become parallel to get this nice smooth movement. That smooth movement means that the transition state energy is going to be the lowest possible. And then the size, then the orbitals, you have to have the big sp3 and the big sp3 opposite each other in order for the orbitals to match up in a molecular orbital kind of way, which we won't necessarily talk about. But that's what it would look like. So I do remember I did that at one point. I did maybe I can cut and paste that video into this one when I process it. I'll put it online otherwise. People that are watching this right now because they didn't come to class, they can watch. I'll put that video online or in the Canvas folder, and then you can watch it. But you should be coming to class. Anyway, we can lecture to both those that are here and those that aren't here at the same time and try and shame them a little bit. Okay? So that's the detailed reason why it has to be anti-periplanar. Okay. And so what that means and we'll do this, we can do the cyclohexane ring first, is that if you have a cyclohexane ring and you have the leaving group like a chlorine, like a chloride, and you put it on a boulder-dashed wedge, and you start to look at the beta hydrogens, let's call this one HA and HB, it turns out that if you do an E2 reaction with a base, with a strong base, that only one of the HA-HB will be removed in the mechanism. So again, this is the alpha carbon, this is the beta carbon, and so only one HA or HB will be removed. It's either HA or it's HB. Well, if we put this into the chair, if I put this into a chair conformation, and I ask, okay, up here, where does the chlorine go, axial or equatorial? If my viewpoint is above the ring, the chlorine should go where? It should go axial, and then down here, HA is above the ring and HB is below the ring. Okay. So now if I'm looking at this, which hydrogen, which beta hydrogen, HA or HB, is anti-periplanar to the chlorine? HB. So HB is anti-periplanar to the chlorine. And that means that for the base to be able to come in and grab a hydrogen, it can only grab HB because HB is the only one that is anti-periplanar. Does that make sense to everybody? So therefore, which beta hydrogen is removed relative to the chlorine? The hydrogen that is trans. So only the trans beta hydrogen is going to be removed in an E2 mechanism. And so when we're looking at rings, when we're looking at cyclohexane rings, and we're doing E2 reactions on them, if it's an E2 reaction, only the beta hydrogen that is trans to the leaving group is going to be the one that's removed. Okay. The other hydrogen will not be removed. Everybody okay with that? So what that means is that if I said, what's the major product if I react this alkyl halide in an E2 reaction, where does the double bond go? Well, if I'm saying write the products of this reaction, and then ultimately it's going to be the major product. But if I just say, what are the possible products of this reaction? First, we have to figure out, well, what are the possible products of this reaction? So we go back to basics. Alpha, beta, beta. We identify our beta hydrogens that can be removed. That's the first step. Step one, find the beta hydrogens. Now, you could say, I don't see any beta hydrogens. Well, that's because we got to draw them in. So for the one up here, there is a hydrogen. And what kind of bond should it go on? A dashed wedge. Down here, there is a hydrogen. It should go on a bold wedge. Right? We had to do that with R and S. Right? I mean, everything builds on itself. So why did we have to do R and S before we do this? Because we needed to understand about the stereochemistry. Okay, so then what hydrogens can be removed? Can I remove HA? Can I remove HB? Can I remove both of them? Well, what's going to dictate that? Is that beta hydrogen anti-periplanar? Better statement, is that beta hydrogen trans? So which beta hydrogen is trans? HA. Can the base remove HB? No. Up over here. Can I twist this molecule to ever make HA anti-periplanar to the chlorine? No. So the base cannot remove HA because the rule is you got to go through an anti-periplanar transition state. If you do not, no reaction. So it will not remove HB. It'll only remove HA, which means that the final product would have a double bond to the methyl group and the other carbon would stay exactly the same with the ethyl group being on the dashed wedge. So our rules for writing the products are going to be a little different in E2. The first step is going to be find the beta hydrogens. That's the same as E1. Second step is going to be which hydrogens can be removed. The ones that can become anti-periplanar. In a cyclohexane ring, it's trans beta hydrogens. Okay. If there was more than one product here that could be formed, then I've got to go to sort of a rule number 3, which says which one's the major product. But in this case, there is only one product, so it's major. The other product is not possible. So I think in Top Hat, they have some of these problems where they're asking you, what's the major product of the reaction? Only they're using a specific base, and we'll have to talk about that. Okay. All right, so this is the rule for stereochemistry for doing E2. The beta hydrogen must be trans. Right. Everybody come with me? Now, I'm going to let's take a step back to E1. So let's just imagine, for the sake of argument, that I did this reaction by E1. So when I do this reaction by E1, I'm going to have my chloride, and I'm going to write this not in a chair conformation, but I'm just going to write it in sort of like a biology sugar type drawing called a Hallworth representation. And then over here I've got my CH3 with my hydrogen down. And then over here I've got my ethyl group down and my hydrogen there. Now, in the first step of an E1 mechanism, I'm going to break my carbon-chlorine bond, and I'm going to end up forming a carbocation. That carbocation is going to have an empty p orbital. Now, the rule as far as it goes with hydrogens, beta hydrogens, are that they need to become planar. So these beta hydrogens, those beta hydrogens must become planar with one of the empty lobes. It doesn't matter which one. But sort of in the same way that when I lose that H+, that orbital is going to become a p orbital and then overlap with the other p orbital, it has to be planar, or I guess in this case coplanar, with the unhybridized p of the carbocation. But as far as stereochemistry goes, it doesn't matter whether the hydrogen is above or below the plane of the ring, because there's two lobes, above and below the plane of the ring. Okay. So when you do an E1, there's no stereochemistry restriction. There's nothing that says, oh, the leaving group has to be, or the hydrogen has to be cis or trans, because once the leaving group leaves, I get a carbocation, and either one can be lost. So the only restriction there is with E2, and that's because of the anti-periplanar geometry that's necessary. So I guess you could call the carbocation coplanar. Okay, but there's no stereochemical restriction. So if I went back to this problem and I said, let's do this problem under E1 conditions, you would get, so if I said, let's react this in E1, what you would end up doing is you would end up getting that product plus you would end up getting the double bond up to the left and down. You would end up with both of those products. Possible. So the other difference between E1 and E2 is the stereochemistry of the beta hydrogen. For E2, it's got to be antiperiplanar in a ring system trans. In E1, it doesn't have to be. You can lose any beta hydrogen because it can always orient itself coplanar to either one of the empty lobes. So these are my two possible products. And in this case, let's call this product A. Let's call this product B. If I called those A and B, which one's the major product? Your choices are A, B, C, both. So which one's the major product? A, B, or both? Everybody got an answer? Okay, we have 19 bolts. And then a couple of A's and B's. So C, both, and that is the correct answer. And if you were thinking, wait, E1, how am I supposed to know what the major product of E1 is? Well, because we talked about it. And E1 is always going to form the most stable alkene. And the most stable alkene is always the one that is most substituted. So this double bond has 3 groups. This double bond over here has 3 groups. Does it matter what the groups are? No. We're back to whatever day it was, Wednesday. Isma? Okay. That's a good question. So when I'm writing that product, I'm writing it looking down on a flat cyclohexane. Whenever you put a double bond in place, remember the double bond, if I'm looking down on the double bond, the other 2 groups have to be like this and like this. In other words, all 4 of those bonds have to be in the plane. So a bold and dashed wedge here mean nothing. Sometimes people want to put bold and dashed wedges there to indicate somehow it's cis or trans. No. When you're looking down a carbon-carbon bond, all 4 groups are going to be in the same plane. Now, if I look sideways on a double bond, then I would have one group towards me, another group towards me, one behind, one behind. But now my perspective is like over here, looking down the carbon-carbon bond, and over here, my perspective is looking down on it. So if I look down on it, I go this way. If I look sideways, I look at it that way. This is the only one where bold and dashed wedges make sense. So that's why it changed. It became planar. Now the other one didn't change, or the other one didn't change from the original molecule. It was bold up here, it's bold there. Same thing over here, dashed, still dashed. So whenever you form a double bond with a ring, all 4 are going to have to be in the plane. Everybody with me still? So, E1, no stereochemistry restriction on the beta hydrogen. E2, yes. So that means as I'm looking at the major product of this reaction, the first step is identify the beta hydrogens. The second step is what are the possible products? In E1, you find a beta hydrogen, you're going to get a product. In E2, got to be a little bit more discriminating that the hydrogen is actually trans to the leaving group. Now, in a non-cyclic system, we basically have a sawhorse. So if I have a sawhorse representation that looks like this, and I've got a hydrogen here, I've got a CH3 here, I've got a CH3, CH2 here, I've got a chlorine, a hydrogen, and a CH3 group, and I say let's go ahead and react this in an E2 mechanism. What are my steps going to be? My steps are going to be, here's my alpha carbon, here's beta carbon number 1, here's beta carbon number 2. If I switch this from a CH3 to a CH2 with an H, those two are my beta hydrogens that could be lost. Now I still have to apply my rule about anti-periplanar. But if you think about this group right here, the CH3, for the CH3, it doesn't matter because you've got 3 hydrogens. The chances of those 3 hydrogens, one of them is definitely going to be anti-periplanar. And if not, I have sort of free rotation around here to make any of those hydrogens anti-periplanar. So my base is definitely going to come in and grab that hydrogen, move that pair of electrons there, kick the chlorine off. So one of the products that I'm going to end up with is a carbon-carbon double bond to the CH2 group. Once the chlorine leaves, I would have a hydrogen up there. So if I'm going to deprotonate this CH2, and I can because, again, there's really the anti-periplanar geometry is given. Then I'm going to end up with the double bond there. What about the carbons? What about the group on the other side? I didn't mess with it, so it's going to have the same as before. Beta? Good question. We need to check that. We need to make it anti-periplanar to write the second product. So this is just the easy product. This is the easy one because it's a CH3. I didn't have to do anything to it. Okay. Now let's deal with the left one. Let's deal with this one. So if we deal with that one, is it anti-periplanar to the chlorine? Well, if you can see that it's anti-periplanar to the chlorine, that's great for you. But if you can't, here's what we need to do. We need to rotate the left and right carbons to put the hydrogen here and the Cl group there. Can everybody see that that's anti-periplanar? Okay, so let's rotate the hydrogen up here. Well, let's put in my bold and dashed wedges. So let's move the hydrogen up there, bring the CH3 group here, and bring the ethyl group there. So all I did was just rotate. I rotated the hydrogen up to the position in the plane, the methyl comes forward, and the ethyl group goes behind. We've kind of done this with R and S. And if I'm looking at it from this perspective over here, we definitely did that with Newman projections. Okay, now I need to put the chlorine down here, so what do I need to do? Rotate the chlorine down to where the ethyl group was. The ethyl group will now go into the back, and the hydrogen will move up into the bolt. So now I've rotated my left and right carbons to make the hydrogen and the chlorine anti-periplanar. Yes. Now my base comes in. Grabs the hydrogen, makes a double bond, kicks the chlorine off. Now here's the critical part of this product. In this product are the methyl groups cis or trans. Because there's two possible products for this alkene. The methyl groups could be cis or the methyl groups could be trans. So which one is it for this mechanism? So when I line the hydrogen and the chlorine anti-periplanar, the base comes in. The groups that are on the bold wedges are going to be cis to each other. The groups that are on the dashed wedges are going to be cis to each other. So over here, I've got a methyl group on the bold. It's going to be cis to the hydrogen on the bold. The ethyl group is on the dashed. It's going to be cis to the methyl group, which is also on the dashed. Because of the anti-periplanar geometry, this is the only geometry of that product that's formed. And in this case, the methyl groups are trans. So we have to orient this hydrogen over here into its anti-periplanar geometry in order to get the proper stereochemistry of this double bond. Does that make sense? Because if I look down that carbon bond, if I looked down that carbon-carbon bond, first carbon I would see would be the CH3. And then that chlorine, let's say that chlorine's there. Right? And then I'd have an H, and then I have like the rest of the molecule. Well, there's automatically a hydrogen that's anti-periplanar to the chlorine. It doesn't matter where I put the chlorine. There's a hydrogen anti-periplanar to it. So these would be my two products, A and B. Those would be my two products of this reaction. Is there a C? Yes. It would be the one where the two methyl groups are cis. Is it possible to form that product? No. Why not? Because that's not the product it forms when I align the hydrogen and the leaving group anti-periplanar. So in the Top Hat book, what you see is you'll see that they give you this reaction, and then they'll give you different products and say which ones, they'll say which one's the major product, but some of them are forbidden products because the geometry doesn't work out. All right? Everybody kind of with me? Let me just take a step back because I saw a number of nodding heads at the beginning. that you could see that this hydrogen was actually anti to that chlorine? It is. Whenever you have, obviously this, to me starting out, this is the easiest way to see that those groups are anti-periplanar. But if you have over here the hydrogen dashed and over here the leaving group bold, or over here the hydrogen bold and the leaving group dashed, that would also make those anti-periplanar. But then you would say, okay, well, how do I know what's cis? The groups with the same bond. Let me think about this for a minute. The groups with the same bond. I'm not sure that the groups with the same bond would be cis. I think you'd probably have to rearrange it. So this way I can guarantee you, if you put it in this kind of conformation, the bolds, cis, the dashed, cis as well. The other one, I'm thinking it might not be the case. So put it in this form. Okay.
So whenever there's a metal and then there's always hydrogen that's like a trans with a hydrogen. So like with the first one, how we had a metal group, and you said like any of the hydrogens.
Oh yeah. That's all. But that there's always a beta hydrogen that's trans. Actually, if let's say there was an ethyl group here, there'd be two hydrogens, and I could align either of those two hydrogens up to be trans. Because there's kind of a free rotation. And then when you come over here, it's like, well, there's free rotation here. I know, that's why I've got to line up the hydrogens. But with two hydrogens, you could line up either one or both. So actually, there's going to be no defined stereochemistry there. You're probably going to get cis or trans or E or Z. There's going to be no one specific that you get, one specific geometry. This with these kind, where the hydrogen starts out on a boulder dashed wedge, you will always get one of two possible products. And this is a boring problem. This is really easy to make. This one, it takes some skill. So this is the more interesting product to make. Now we're going to do this again next semester when we do Hoffman elimination. And so I'll introduce the idea of the Hoffman term, but the Hoffman reaction that's going to be next semester. So like I'm still remembering the fact that I just did this like 2 or 3 months ago in the summer class. And then when I was doing it, I'm like, did we go over this already? And no, because we went over it in the spring class. So it's all kind of runs together. But let's define the Hoffman product in a moment. Okay. So now the question is, for this reaction, I can form either A or B. Which one am I going to form? It depends. Well, that's not a very helpful answer. It depends. But it depends. On what? On the base that I use. So whenever we do E2, we need a strong base. So your book uses as its favorite strong base sodium ethoxide. So this is a deprotonated ethanol molecule. By definition, an O- is a strong base. This is even stronger than hydroxide. So this sodium ethoxide is a strong base. And that's what you need. It is also called a small. I call it a small strong base. because it's not sterically hindered. It's not my favorite, because the difficulty here is every strong base is a strong nucleophile. So every time you have a strong base, you have a strong nucleophile, which leads us into the gray area of, is it going to react as a base or is it going to react as a nucleophile? And if the answer is both, then all of our rules are just down the drain. So before we get to that point, let's just say this is going to be a strong base for the moment. So that's a strong base. Now, in my problem sets, you'll see that I use NH2 minus in my video. And the reason I use NH2 minus is because, number one, NH2 minus is stronger than O minus, because remember it goes FOCN, or no, FONC. So as I'm going from right to left, a basicity increases. So an N minus is stronger than an O minus. And there's something about NH2 minus, which is beyond the scope of this course, that makes NH2 minus not be a nucleophile at all. So I like NH2 minus as a strong base because that's all it does. It doesn't act as a nucleophile. So you'll see both. The book will use ethoxide. That's its favorite. It will also use, you'll see that they use ethoxide in ethanol, which is actually the historical way to make ethoxide. You take ethoxide, you dump a piece of sodium metal in it, a small piece of sodium metal, hopefully it doesn't catch fire, and then you get sodium ethoxide dissolved in ethanol. It's the same reaction when you take sodium metal and you react it with water. Remember, you get H2 gas and then sodium hydroxide. Take that reaction, replace an H with an R, and you have how to make alkoxides. The sodium is a counterion. You can erase it if you'd like. I'm hesitant to show it simply because then it shows up in the worst was it showed up in the middle of a cyclohexane ring. No idea how a sodium plus ion gets in the middle of a cyclohexane ring. So it's why I don't normally show metals, because they end up everywhere except where they should, which is a counterion to a negative charge. So, small base. What happens with the small base? Well, with the small base, my choice is to remove two hydrogens. So let me write this molecule without the stereochemistry, just to make it a little bit clearer. We had a hydrogen, we had a chlorine, we had a CH2 with a hydrogen. Over here we had a carbon, I had a carbon there. We had an ethyl group, we had a methyl group, and we had the hydrogen there. So these were the two hydrogens that were being removed. What type of hydrogen is this? Primary, secondary, or tertiary? Time's up. Take a guess. Someone take a guess. Good guess. It's tertiary. What kind is this? What kind of hydrogen is that? Primary, secondary, or tertiary? Primary. Which one of those two is more sterically hindered? Tertiary. So, if I have a small base, like ethoxide, like NH2 minus, the small base can get to either one of these two hydrogens equally well. Everything in chemistry happens because of a reaction coordinate diagram and an energy. So what that means is, that means that the transition state energies between the base, small base, removing the primary or the tertiary, they're going to be roughly the same. So what's going to dictate the major product? What's going to dictate the major product is one product is going to be more stable than the other. And so which one of those two products was the more stable? Well, if we go back here for a moment, we'd be able to tell, okay, which one of these two products is going to be the major product because it's more stable. So if we go back here, which one is it, A or B? Which one is more stable? B. B is more stable. So B is more stable than A. That means that this would be the major product if I use the methoxide ion, or, well, in this case, an ethoxide ion. I use a small base, I get the same product as E1. Right? I get the most substituted product. Why? Because the sterics, a small base, it can get to either place. So there's always this yin and yang of organic chemistry. The reason organic chemistry is useful is because I can do this, I can do that. And this is the first time where I can say, you know what, I want to make product A. I have a reagent to make it. I want to make product B. I have another reagent that'll make it. And so what kind of base will make A only? A big base. So we'll start on Monday with tertiary butoxide, large sterically hindered bases. Okay, I released chapter 11 this morning. I would like you to go through chapter 11. We will finish up chapter 10 on Monday. Chapter 11, hopefully as you're reading through it, is a review of all the stuff that we've done. Because what they're doing in chapter 11 is they're comparing and contrasting SN1 to SN2, E1 to E2. And so hopefully as you read through that, it makes sense. Okay, I did get a couple questions on chapter 10 problems, which I posted on Piazza. Email me more questions. I will answer them over the weekend. And I will have your exams on Monday to hand back. And the answer key will go up on Monday as well. Remember, your practice problems are also due on Monday.